angles having unequal measurements. So therefore, we have to use our properties of inequality. So before, we focused a lot on things being congruent triangles, congruent segments. Now they're not necessarily going to be congruent. One segment might be greater than the other. Another angle might be less than the other, things like that. So we have a few properties of inequalities that we're going to discuss. These are just kind of, I don't necessarily expect you to have these like memorized, but I want you to be able to apply them because these are just like generic with any number. So a couple things to keep in mind. If A is greater than B and C is greater than or equal to D, then A plus C has to be greater than B plus D. Hopefully that's pretty intuitive. If A is greater than B, if you add C to A and you add D to B, it would still have to be greater than. So these are just applying them with any type of numbers or measurements. If A is greater than B and C is greater than 0, then A times C must be greater than B times C, and A divided by C must be greater than B divided by C. So something else to keep in mind too, C has to be greater than 0, right? Because we can't divide by a negative number there. And if we multiply by a negative number, it won't be greater than, it'll be 0, and then we'd have to have or equal to. If A is greater than B and C is less than 0, then it's just flipped around. A times C would be less than B times C, and A divided by C would be less than B divided by C. If A is greater than B and B is greater than C, then A has to be greater than C. That's almost kind of like the transitive property, if you think about it. That's like the transitive property, but with inequalities. If B is greater, or if A is greater than B and B is greater than C, then A must also be greater than C. And then last one, if A equals B plus C and C is greater than 0, then A must be greater than B. So again, I don't necessarily expect you to have these memorized. It's more being able to apply them if I give you actual like measurements or actual diagrams. And then we have just one theorem for this part. It is the exterior angle inequality theorem, and it says that the measure of an exterior angle of a triangle is greater than the measure of either remote interior angle. We had another exterior angle theorem that was just the basic exterior angle theorem, and that had to do with the exterior angle in a triangle. It looked something like this. So if you have your triangle and you have an exterior angle, like one of those sides gets extended with an auxiliary line. Let's say I said this was triangle ABC. Then the theorem we learned before is that your exterior angle, I need to label this as well, call this D. Your exterior angle, BCD, has to be equivalent to the sum of the two remote interior angles, right? The measure of angle BCD has to equal the measure of angle B plus the measure of angle A. Well, then kind of using those theorems we just talked about above, that then implies that the measure of angle BCD has to be greater than the measure of angle A and greater than the measure of angle B. So that's what this theorem says. So based on what we know about our exterior angles, the measure of angle BCD has to be greater than the measure of angle A. 7. And it also has to be greater than the measure of angle B. So now we're just really going to apply these with a couple true-false things. Again, these properties are mainly application-based. So if you take a look, we have a few true-falses. This says if the measure of segment XY equals the measure of YZ plus 5, then the measure of XY has to be greater than the measure of YZ. Do we think that that would be true or false? If XY equals YZ plus 5, then XY has to be greater than YZ. Ella says true. Do we agree? All right, I see some head nodding. I see some thumbs up. Yes, This is definitely true. That's definitely true, because also too, you got to think about, we're dealing with measurements, right? So are these going to be negative values? If they were negative values, it'd be a different situation. But in order for these to add to equal xy must be greater. If the measure of angle A equals the measure of angle B plus the measure of angle C, then the measure of angle B must be greater than the measure of angle C. Peyton and Braden are vigorously shaking their heads no. Do we all agree with no or false? All right. False. Yes, I agree. This is false. There is nothing here to say that B is greater than C or C is greater than B. They just have to add up to be A. So we don't know. If the measure of angle H equals the measure of angle J plus the measure of angle K, then the measure of angle K must be greater than the measure of angle H. David is saying no. Braden is vigorously saying no and giving it a big thumbs down. Julie is giving it a big thumbs down. Do we agree? Is this false? That is absolutely false. What would be true? How could we change it to make it true? Yeah, if you flipped the statement around, if you said measure of angle H was greater than K, then it would be true. Good, and then if 10 equals y plus 2, then y must be greater than 10. What do we think? Yeah, that's a big thumbs down. This is false. So very similar to the algebra things that we did, just applying inequalities. So you got to remember less than, greater than, how that would work. I threw a little proof in here so we can practice what this would look like, because we're going to be able to use these properties in our proofs, just like we could use the properties of algebra, like the addition property of equality, things like that. You'll be able to use these properties. Luke, why are we doing a proof, or why to something else? So complete the following proof. We are given that the measure of AC is greater than the measure of BC. So this side basically is just telling you the measurement of this side is greater than the measurement of this side, and the measurement of CE is greater than the measurement of CD. All right, so it wants us to prove that the measurement of AE is greater than the measurement of BD. So let's just step away from the proof real quick, and let's just see this kind of logically. If we know that this segment here is greater than this segment, and we know that the measurement of this segment is greater than the measurement of this segment, if you take two values that are larger and combine them into one full segment, isn't that going to have to be larger than the other segment? That's basically what this proof is doing. It wants you to prove that this entire segment here, AE, is greater than this entire segment here, BD. Well, isn't segment AE made up of larger parts than segment BD is? So if we add those parts together, it's going to still have to be bigger. That's basically what we're doing. Just think about it in terms of numbers. It's the same thing. AC here technically just represents a measurement. So we're going to throw in our given. So say the measure of AC is greater than the measure of BC, and the measure of CE is greater than the measure of CD. That is given, and we want to prove that the measure of the measure of AE is greater than the measure of BD. So what we need to do, this is actually really similar to the segment proofs we did back in first quarter. We need to be able to say that this entire segment AE is greater than this entire segment here, BD. Wasn't that made up of smaller parts? So what are we probably going to have to do to combine our smaller parts together? Yeah, segment, yeah, segment addition, but absolutely. We're going to do that in our third step, actually. We are definitely going to have to use some segment addition, and we are going to have to, well, I guess it doesn't really matter which one you do it in. We'll do that first, actually. Why not, Peyton? We're going to do that part first. So what we are going to do is our segment addition postulate. We need to get segment AE in there. So we're going to say that the measure of segment AE is equivalent to, and then we're going to take our smaller parts and add it together. The measure of AE is going to equal the measure of segment AC plus the measure of segment EC. Or I guess, wait, we should name it the same way it's named in the given, and I need to write smaller. I write too big. So the measure of segment AE equals the measure of segment AC plus the measure of segment CE. And we can do that with the other segment right here. We can say that the measure of BD equals the measure of BC plus CD. And that is the angle addition, or the segment addition postulate. Why are we yelling about grammar in the chat? What's happening? This isn't grammar class, Nick. There is no grammar class, children. You're in high school. We hopefully learned that a while ago. Okay, but I've read your guys' emails. Our grammar is a little questionable. All right, segment addition postulate. Actually, not everyone's. I get some very lovely composed emails from my GT students. It includes the Dear Mrs. Geyer and everything. And I'm like, you guys, someone taught you well. Anyway, sidetracked. So we got our segment addition postulate. That's great and all. But how in the world am I now going to get AE is greater than BD? How am I going to get those things together in one inequality? Any ideas? I would maybe take a look at some of our properties up here. Is there a property that could help us? Anybody? The fifth property, maybe 1, 2, 3, 4, 5. Oh, you're with this one with the adding. We do want to do some adding. But if you take a look, we have that one measurement's greater than the other, another measurement's greater than the other, and we got to add some stuff together. If we take a look, that's actually a lot like our first property here. What we can do is if we know A is greater than B and C is greater than D, if we add a measurement on one side and a measurement on the other side, isn't it still going to have to be greater than? That's what we're going to do. So what we can do here is we need to be able to say that in order to say AE is greater than BD, we have to show that AC plus CE is greater than BC plus CD, because those are our little parts that it's made up of. So basically what we're going to do, and because we've already done our segment addition, hopefully it'll be a little easier to see. We're basically going to take CE and add it on the left, and we're going to take CD and add it on the right. Because if we're adding measurements on either side there, it'll still stay greater than. You guys in the chat, I wonder, I'm going to disable the chat, children. All right, so what we're going to need to do here is say that the measure of AC plus CE is greater than the measure of BC plus CD. So again, what I basically just did, pay attention, quit looking at the chat, look at this. What we need to do, is add the measure of CE on the left, and we added the measure of CD on the right, because if AC is greater than BC and you add a greater measurement on the left, right? And something that's less than on the right, it's still going to be greater than. Does that kind of make sense? I lost you, David, didn't I? Okay. You're too busy looking at the chat. So. Okay, well here, let's make it into numbers. All right, so let's give you some numbers to look at. Let's say I magically told you, I'm going to magically put some numbers in there, just numbers I feel like saying. So let's say I told you the measure of AC, I don't know, was 10, is greater than the measure of BC, which is, I don't know, how about 7? Okay, 10 is greater than 7. We got that? Cool, okay. Then let's say I told you the measure of CE, and these are just generic numbers. It doesn't really matter because it doesn't tell us our triangles are congruent or anything like that. And then let's say I told you the measure of CE was 3 is greater than the measure of CD, which was 2. So that means AC is 10, BC is 7, CE is 3, and CD is 2. Just picking out numbers. Well, if I add 10 plus 3, I'm going to get 13, right? And if I add 7 plus 2, I'm going to get 9, right? Wasn't 13 greater than 9? That's basically what we did, except instead of numbers, they were like segment names. Does that help a little, David? Yes? Okay, cool. So yeah, because if we, so to get AC, you add up your little parts. To get C, or I'm sorry, to get AE, we add up our little parts. To get BC, we add up our little parts. And if you add 10 plus 3, it's going to be still greater than 7 plus 2. Better? Yes, yeah, and actually what you have to do, all you have to do, which is real nice in my opinion, they don't have names like the Angle Edition property did or anything like that. Oh my gosh, why isn't my eraser working? Hold please. So all you actually, I'm gonna throw my computer out. All you actually have to do is just put a property of inequality. They don't have like their own specific names. You don't have to be like property 1 of inequality or things like that. This is just, it is a property of inequalities that you can say if I add this value to the left and this value to the right, it's still greater than. So we can just say property of inequality. And you're welcome to abbreviate inequality if you want. And then for this last part, if I can say the measure of AC plus CE is greater than the measure of BC plus CD, and I knew here that here I did my addition, right? What's going to let us say that AE is then greater than BD? Which property? This one's just a property we've been using all year. Substitution, yeah. And you could do these in the flipped order too. The flipped order is probably a little bit better just for your logical process, but this would be substitution. Good. Okay, so I just wanted to show you guys that to show you if you need to use one of those properties of inequality, you simply just say property of inequality. All right, so we haven't talked about contrapositives yet, Luke, don't worry. All right, so on to 6.2. During quarter 1, we talked about conditional statements. Remember, those are our if-then statements. If our hypothesis, then our conclusion, and they were abbreviated to if P, then Q. So P is your hypothesis, Q is your conclusion. We also learned about the converse, which converse means reverse. If Q, then P. If your hypothesis, then your conclusion. Sometimes these statements were true, sometimes these statements were false. Typically, your conditional statement is true. Your converse does not necessarily have to be true, because when you reverse the order of a statement, it means something different. Something that you're going to be looking at with these during this chapter is you look at them kind of as Venn diagrams, like Venn diagrams where they overlap, right? They're going to share those properties. So these are kind of looked at with some Venn diagrams. I'm going to do my best to draw some Venn diagrams here for you. So conditional statements, we use this Venn diagram, and this is in your textbook on page 208. So you're going to see these same Venn diagrams on page 208 in your textbook. So we have our nice big circle here. We're going to put Q. So this is our conclusion, and then inside is P, which is our hypothesis. This is for a conditional statement. If P, then Q, because if your hypothesis, then your conclusion means if your hypothesis is true, then your conclusion has to be true, right? And if your hypothesis is true, let's say you had just some statement, whatever it is, it doesn't matter. If your statement is sitting inside of P, it's a true statement, then since Q is surrounding it, isn't it also then technically inside of Q as well? Okay, so if it's true for your hypothesis, then it's true for your conclusion. But let's say you switch that around. Just because something is maybe true for your conclusion, maybe your hypothesis is false, not with a conditional statement, but I'm going to show you what that means in just a second. All right, so that works. This Venn diagram is what you're going to see for if P, then Q statements, and one other one, we just haven't talked about it yet. Converse is if Q, then P. So for your converse, the Venn diagram is actually flipped around. So for a converse, you actually have this the other way. P is on the outside and Q is on the inside. Because if it's true for Q, my Q looks very sad. If it's true for Q, it has to be true for P because your statement is flipped. All right, now we're going to learn about two new ones, inverses and contrapositives. Oh, thank you, Sydney. Except, yeah, my next one was bad. I know. Listen, you come and write with this stylus and then see how you draw. Yes, very focused, Logan. There is no attention deficit happening at all with any of us, me included. I'm very focused. All right. Anyway. Inverse and contrapositive. So inverse is if not P, then not Q. When I say not, think like a negation, right? And sometimes the statement, you simply add the word not into it. If two lines are not parallel, then they whatever, right? You can literally put the word not in it. I can read you a good example here. So let's say I said, if a student is a runner, then they are an athlete. That would be a conditional statement. If a student is a runner, then they are an athlete. If P, then Q. The inverse of that, you take it and you negate it. If a student is not a runner, then they are not an athlete. Now, is that necessarily true? If a student is not a runner, does that automatically make them not an athlete? No, maybe they're on the football team, maybe they're on the swim team, maybe there's something else. So just because a conditional statement is true does not mean its inverse is. A contrapositive is actually the negation of the converse statement. If not Q, then not P. So again, if your original conditional statement was if a student is a runner, then they are an athlete, you switch it around and you negate it. So if a student is not an athlete, then they are not a runner. Okay, that would be true. If they're not an athlete, then they certainly don't run. Okay. So these Venn diagrams actually also apply to some of these shapes. So I don't know if you noticed when I was just talking about it, if a conditional statement is true, the inverse actually is false. And if a conditional statement is true, then the contrapositive is also true. So that's important with this part down here, these two little other notes I made. A statement and its contrapositive are logically equivalent. Logically equivalent means they're both true or they're both false. So if you have a true conditional statement, then you are going to have a true contrapositive. Or if you have a false conditional statement, you're going to have a false contrapositive. A statement is not logically equivalent to its converse or its inverse. So just because you have a true conditional statement does not mean the converse will be true and does not mean that the inverse will be true. So these Venn diagrams can also be used for our new statements. So the if P then Q Venn diagram can also be used for our contrapositives, because conditionals and contrapositives are logically equivalent. If one's true, the other's true. So this one works for if P then Q, and it also works for if not Q, then not P. Because again, the conditional and the contrapositive are logically equivalent. The other kind, that works for a converse and the inverse, because the converse and inverse are then logically equivalent because it's the opposite of the others. So this works for if Q, then P, and it works for if not P, then not Q. Okay. So this, you'll have to, once you see some statements, if you're a little confused, I think that will help. The Venn diagrams, I'm personally not a huge fan of the Venn diagrams, but they're supposed to be a kind of a visual representation for you. And some of the questions on the homework do ask you about that, so I wanted to make sure we talked about it. And really, we just have a couple examples and then we're done. We should be done early, which is awesome, since we're so focused. All right, so some examples, write the inverse and the contrapositive of each true conditional. So this is just practicing writing it. I have faith that we can do this. However, if we can't do the basics, then we certainly can't do the hard stuff. So if a parallelogram is a square, then it is a rectangle. That is our true conditional statement. If P, then Q. So our hypothesis is a parallelogram is a square. Our conclusion is it is a rectangle. Absolutely, that's 100% true. And I'm even going to write down, just so we don't forget, this is certainly a true statement. Based off this statement, I'm going to draw us a Venn diagram just so you can see how it works then for your homework. So in this situation for your if P then Q, your Venn diagram would look something like this. Sydney, that's a nice circle that I drew. And then inside we'd have our other one. That was also nice. So we are going to have our rectangle, because that is our conclusion, and then our hypothesis is a square. So this is true because if a parallelogram is a square, then it's falling in this inside circle. Right? If a parallelogram is a square, it falls inside that in that interior circle, which is also going to make it a rectangle. So now the inverse, our form there is if not P, then not Q. So we need to take our statement and negate it. So if a parallelogram is not a square, then it is not a rectangle. Ooh. So if a parallelogram is not a square, then it is not a rectangle. Do we think that would be true or false? I'm seeing some thumbs down. That would be false. I agree. That would definitely be false. If a parallelogram is not a square, then it is not a rectangle. Again, think of it in terms of your Venn diagram. Just because it doesn't fall in the square category, couldn't it just fall in the rectangle category? Yeah, just because it's not a square doesn't mean it's not a basic rectangle. And then contrapositive, that is if not Q, then not P. Who thinks they can tell me how we would write this statement? Julia, what do you think? Yep, exactly. Ooh. If a parallelogram is not a rectangle, then it is not a square. What do we think, true or false? Thumbs up, I agree. This would definitely be true. And remember, from the previous page, if your conditional is true, isn't your contrapositive going to be true? And if your conditional is true, your inverse is false. Remember, think logically equivalent versus not. And again, think about it with your Venn diagram. If a parallelogram is not a rectangle, if it's not a rectangle, is it even going to fall inside our diagram at all? Right, if it's not a rectangle, then it's going to be somewhere out here. And if it's not a rectangle, then it's certainly not a square. Okay, so that's what that means. Luke, does that answer your question? Do you now know what a contrapositive is? Okay, good. All right, and then last thing, this is again just to think about our logically equivalent versus not. A certain conditional is true. It's true, it doesn't matter what it is. If said conditional is true, must the converse be true? You can take a look at the front if you need to. Remember what's logically equivalent and not. So if the conditional is true, must the converse be true? Julia says no. What do you guys think? Luke says no. Logan says he's not sure. Okay, a couple people, Lucas says no. So this would be that part that's on the front. A statement is not logically equivalent to its converse or its inverse. So if the regular conditional statement is true, the converse does not have to be true because they are not logically equivalent. So we would say no. Must its inverse be true? Is the conditional and the inverse, are those logically equivalent? I see a few no's. Yep. This one is also a no. That's the same statement that's on the front of the notes. A statement, and when it says a statement, it means a conditional statement. So a conditional statement is not logically equivalent to its converse or inverse. What about the contrapositive? Is it conditional or is it logically equivalent to the contrapositive? Yes, this part would be true. This part is a yes. Okay.